Hello everyone. So we have seen Terzaghi's bearing capacity theory. The general equation Q equal to C N C plus Q N Q plus 0.5 gamma B N gamma. That is the ultimate bearing capacity that you have seen. So there is the ultimate bearing capacity equation. As per Terzaghi's, it is CNC plus QNQ plus 0.5 gamma B N gamma. So NC, NQ, N gamma are bearing capacity factors, and these are all functions of phi, shear parameters, and C is cohesion parameter. So here NQ, NC, everything will be known to you when you try to solve any problem, because it is already given in the form of a chart, and knowing this value from shear test, you know the value of C and phi, so you can substitute. Q is the surcharge at the level of base of the footing, and it is given as gamma times depth of foundation, and B is the width of the footing. So this is the general equation for a continuous footing, and the failure is going to be general shear failure. If it is local shear failure, I have already told you, you need to modify C, you need to modify phi value. So C and phi both has to be modified, and accordingly for the modified value of phi, you should find out the bearing capacity factors, and that should be substituted. So C will be modified, phi will be modified. So that should be substituted. If you want to find out the net ultimate bearing capacity, is called net ultimate bearing capacity, then it will be C and C plus Q and Q plus 0.5 gamma B N gamma minus the surcharge should be removed, so minus Q. So finally, if you simplify it, this is equal to C and C plus Q can be taken out, Q into NQ minus 1 plus 0.5 gamma B N gamma. So this is called the net ultimate bearing capacity. And the safe bearing capacity, you know, can be found out if you know net bearing capacity Q and U divided by a factor of safety 0.5 to 3 plus gamma times df. These things I have already explained to you how to find out the safe bearing capacity. So you can find out the safe bearing capacity. And if you know the safe bearing capacity, what is the safe load your footing can carry will depend upon the safe load that a foundation can carry will depend upon the safe bearing capacity multiplied by foundation area of the footing. So area of the footing you multiply it, you know the safe load that your foundation can carry. But this equation, as I have already told you, will be valid for strip footing, is valid for strip footing. So for other shapes, you will have to modify it. So let us modify it. So let us modify it. So what is the modification due to shape? So for various shapes of footing, the ultimate bearing capacity is going to be CNC plus Q and Q plus here you will have to multiply it by 1.3. So it becomes 1.3 CNC plus QNQ plus 0.4 gamma B and gamma for a square footing. So if the footing is a square footing and not a continuous or a strip footing, then this equation should be used. Then QU equal to 1.3 times CNC plus QNQ plus 0.3 times gamma B and gamma for circular footing. So if the shape of the footing so these are some of the modifications due to shapes. So for other shapes, these modifications must be made to the equation, and then only you can apply it for square footing or circular footing. Also, it doesn't take into consideration the water table effect. So this equation is a very general equation given by Terzaghi, and you will have to again take into consideration the effect of water table. So this equation 1 will be modified now. If I call it this as equation 1, so for water table effect, you will have to modify it. So what is the water table effect? Water table effect. The bearing capacity due to water table effect, the ultimate bearing capacity will be equal to C N C plus Q N Q into, you will have to multiply it by a factor due to water table RW1 plus 0.5 times gamma B N gamma multiplied by another water table correction factor. So RW1 and RW2 are called water table correction factors. So if this is the footing embedded into the ground, this is the ground level, and the water table is very, very deep, the size of the footing is B here. So, if this depth of water table is greater than B, this is the depth of the footing, no correction is required. For this case, the water table is at greater depth than from the base of the footing greater than B. Say B equal to 1.5 meter. And so from the base of the footing, the water table is below the base, this 1.5 meter, greater than equal to this. Then you don't require any correction factor. The correction factor for that correction factors will be 1. So if for very, very deep level of water table greater than B as shown in the figure, from footings base greater than B as shown here, then RW1 will be 1, RW2 will be 1. No effect. But if this water table is at a depth which is less than equal to B, then you need to make the corrections. And water table correction, the formula you will have to remember. So here what you are finding, that water table is at shallow depth from the base of the footing less than equal to B, then RW2 is going to be equal to 0.5 into 1 plus, say this depth is ZW2. This depth is depth of water table below the base of the footing is ZW2, then this becomes ZW2 divided by B. For ZW2 less than equal to B. So less than equal to B from where? From the base of the footing. From footing base. From here. So ZW2. This equation is to be, say the water table is say just touching and RW1 will be 1. So the equation for RW1 is 0.5 1 plus ZW1. I will tell you what is ZW1 divided by depth of foundation. So depth of foundation is here, and say water table is somewhere here. It comes up very near to the groundwater table. So it is going to be up to DF. So ZW1 here for RW1, the ZW1 will be between 0, that is up to ground level. So 0 less than ZW1 is less than equal to DF. So it is in the range of from ground level to the base of the footing, and this is the formula. So you can, if this is the case, when the water table is below the base of the footing, then in that case RW1 for this particular case, see the figure, if I call it this figure 1, for figure 1 case, the water table is here, ZW2, and ZW2 is less than equal to B. So you just use this RW2 and RW1 will be equal to 1. Because here the condition is ZW1 is less than equal to DF. Now the ZW1, because the water table is deeper below the base of the footing, it is below DF, so it becomes the maximum value 1. So RW1 for this case will be there. Now I will take another case. Say the water table is going to touch the base of the footing. So water table is here. The water table is touching the base of the footing. So water has come up and touching the base of the footing. Then in that case ZW1 equal to DF. For this case, let's say figure 2. So for figure 2 case, RW1 will be 1 because ZW1 equal to DF. From the ground level, the water table is at a depth of DF. So ZW1, the water table is at a depth of DF. So if you substitute here DF by DF equal to 1, 1 plus 1 equal to 2. If you multiply it by 0.5, it becomes 1. So RW1 equal to 1 for case 2. And for case 2, RW2 can be computed. It is 0.5 1 plus ZW2. What is ZW2? ZW2 is always taken from the base of the footing. So ZW2 equal to 0. So if ZW2 is equal to 0, then it becomes 0.5 into 1 plus 0 by B. Because ZW2 is, water table is touching the base of the footing, and therefore ZW2 is always measured below the base of the footing, therefore it is 0. So 0 means it is going to be 0.5. So the maximum value of RW2 is 1 and minimum value is going to be 0.5. The maximum value of RW1 is here. So RW1, I will take a case and then calculate it. So water table correction factor for water level somewhere here. So water level, let's say it is here. So ZW1, the depth of water table is now less than DF. It has gone up. So ZW1 is less than DF. So you can substitute the value of ZW1. But ZW2 is going to be 0 because it is measured, ZW2 is measured below the base of the foundation, and here it is going to be 0 because water table has gone up. So this this becomes 0 and 0.5 into 1, this becomes equal to 0.5. So these two equations are very, very important, and it is the water table effect that you will have to multiply it and calculate it for various conditions. I will solve some of the examples and let you know how these things can be calculated. If you solve more problems over this, you will be able to learn the effect of water table, shape effects, if it is not general shear, local shear failure, how to use all those things can be explained in the next video, so that your all theoretical concepts you learn it in much better way. Thank you very much.